Hello class, I'd like to go over relative velocity again, just to give people another chance to hear an explanation of it. So let's get right to it. We start with our boat that's traveling across the lake. The river has a current that's traveling east, and there's a box or a rock, this black thing on the side of the lake or side of the river that's going to be where we're standing. We've got this person in the boat. They're going across the lake. The water's flowing east. Now, after some time, you can imagine what would happen is the boat is not just going to go straight across. It's also going to go to the right because the current of the water is moving to the right. And so you can imagine that if you're standing here at this black rock, you would see the boat go away from you and also to your right. And a lot of times these questions want you to find out, well, how far away is the boat going to be from where you're standing? Or how fast is the boat going away from where you're standing? Well, this is a complex motion because it has to do with two different things. It has to do with the motion of the boat, and it also has to do with the motion of the water. Let's imagine instead we have the person who's leaving on the boat, but right before they leave, they put a little flotation device and they drop it into the water. Okay? Now, that flotation device is just going to move with the current of the water to the right, and the boat is going to move away from the flotation device. So, let's say that we know the distance of the float from where it started, and we know the distance of the boat from this float right here. This distance is 3, and this distance is going to be 4. Can we figure out how far away the boat is from where we started? Okay, yes you can, right? You use Pythagorean's theorem, and it works out in this case to be 5 meters. Now, what we've done here is we've broken this boat motion into two parts. We've looked at the distance that the boat has traveled away from a floating object, and then we've looked at the distance or the displacement of the floating object from where we started on the Earth. And we saw that if we add the two together, we actually get our answer right here. And so we're measuring the boat with respect to the floating device, which is why I wrote the displacement of the boat away from the floating device. Here we have the displacement of the floating thing, or buoy, away from the Earth. And we found that if we add those together using vector addition, we actually get the distance of the boat away from the Earth right there. Now let's say that this all happened during 1 minute of time. So the float moved to the right by 3 meters and it moved upwards by 4 meters in 1 minute, and so overall the boat is 5 meters away from the starting point after a minute. So we wrote an equation down here that relates the distance of the boat from the floating device, the distance or displacement, I should be saying displacement, the displacement of the float from the Earth, and if we add those together, we get the displacement of the boat from the Earth. If we go ahead and we divide each of those by 1 minute, which is how much time has passed by, okay, and then we simplify, we see that when we divide displacement by time, we get velocity. And so we know that the velocity of the boat from the Earth is equal to the velocity of the boat from the floating device plus the velocity of the floating device from the Earth. And we know that since both of these velocities have direction, we just can't add the values of the numbers together. We have to use vector addition to sum them together in order to get the velocity of the boat from the Earth. Okay, so this is actually why this is called relative velocity, because we're adding two different relative velocities together. The velocity of the boat relative to the float, and then if we take the velocity of the float relative to the Earth, we can get the velocity of the boat relative to the Earth. So we're kind of using two different reference objects here. We know the motion of the boat in reference to the float, and we know the motion of the float in reference to the boat, or in reference to the Earth, rather, and we'd like to know what is the motion of the boat in reference to the Earth. And it turns out that you can add those together to give you this new velocity here. One place where relative velocity is really important is when we're studying the solar system and objects in the solar system. So astronomers use it quite a bit. And the reason that it's so important is because let's say we're all on the Earth, obviously, and we want to know something about the orbit of Jupiter. Now, every measurement, or almost every measurement we've ever made of Jupiter, is we're measuring it from Earth. So we look at Jupiter from Earth, and we can see how far away Jupiter is from Earth, how that distance changes as time goes by. Well, it's tricky to measure how far away we are from Jupiter, but it can be done. But we can also measure how fast Jupiter's moving, but we're measuring it from our spot on the Earth. And so the velocity that we're measuring of Jupiter is measured using distances that are measured from Earth. So the velocity of Jupiter is measured from Earth. Now, what scientists would like to know when they're thinking about Jupiter is, well, how is it moving around the sun? What's its speed as it moves around the sun? So really what astronomers want to know is, what is Jupiter's speed as measured from the sun? So we have two different reference points that we're looking at Jupiter from. We're looking at it from the Earth, and then we'd also like to know, what is it doing? What is its speed if we measure it from the sun? Well, what's the missing piece here that we would need in order to, if we know this and we want to know this, what else do we need to know to get this? So think about it for a couple seconds. Okay, what you would need to know is, well, what is the velocity of the Earth, this spot, with respect to the sun? And so if you know how fast the Earth is moving, this reference point is moving from the sun, and we know how fast Jupiter is moving from the Earth, then we can add them together and we can figure out how fast Jupiter is moving from the sun. So we need to know the velocity of the Earth with respect to the sun. And then if we use our equation, okay, I know the velocity of Jupiter as measured from Earth. I know the velocity of the Earth relative to the sun. And if I add those together using vector addition, right, these are vectors because they have a direction and a value, then I can get the velocity of Jupiter as measured from the sun. So, and if you remember, our trick here when you're adding them together is, if you want to get rid of this reference frame, so if you want to measure Jupiter from the sun, you've got to make certain that your values are kind of the inner subscripts. So if we know the motion of Jupiter from Earth, and then we happen to also know the velocity of the Earth from the sun, then we can figure out the velocity of Jupiter from the sun. And so that's our trick here. If you ever happen to, let's say you knew the velocity of Jupiter from Earth, and then you knew the velocity of the sun from the Earth, okay, we couldn't add VJE plus VSE because my inner subscripts aren't working. Now, the nice thing is that the velocity of the Earth from the sun is just the opposite of the velocity from the sun is measured from the Earth. So we would just put a negative sign in there and that would fix it. But this is why we're talking about, this is why this is called relative velocities, because we have velocities of objects relative to a couple different things. And if we know the velocity of something relative to one thing and we want to switch it, so we want to know the velocity of this with respect to something else, we can use this vector addition to help us. So let's take a look at a slightly different, another problem. So in this case, the person heads out from the starting position again. They're going to put that float back in the water, but this time they want to go straight across the lake. So their distance from the Earth, they want it to be, or their displacement from the Earth, they want it to be straight north. That float is still going to move uh, to the east. So you can imagine, well, what's going to happen here? Well, we know that the float is going to move east, so the displacement of the float from the Earth is this arrow right here. What is the boat going to have to do if we measure it relative to the float in order to give us this straight line? Think about that for a couple seconds. Okay, the boat is going to have to move both away from the float and also to the left of the float so that it gives us this straight line right here. Okay, so the displacement of the boat from my floating object is just going to be away and to the left. Okay, did I say to the right before? I might have, but I meant it's going to have to go to the left. So if we write our equation again here, right, that just relates all of my vectors together. And you can see we're measuring the boat with respect to the float. Here we're measuring the float with respect to the Earth. So I have two different reference points I'm using. The Earth for measuring the floating object, and I'm using the floating object to measure the boat. And then if I add those together, I can get the boat measured from the Earth, which is pretty convenient. So let's just see if we wanted to solve this problem. I did my sketch up here, and then I wrote my knowns and unknowns. I know that the boat measured from the Earth, we don't know how fast it's going to go, but we know the direction needs to be north. If we measure the boat from the float, all right, I know, I didn't tell you beforehand, but the boat's going to move at 10 meters per second, but we don't know the exact direction. We know that it has to move up and to the left, but we don't know the exact angle. And then we know that the floating device with respect to the Earth is moving at 6 meters per second east. So my equation is going to be, again, what we have right here. And then let's see what we can do for a solution. So I drew my vectors back up here. I've got my float measured from the spot on the Earth. I've got my boat measured from the floating device. And then I know that when I add those together, it's going to give me my boat with respect to the Earth. I put in an angle theta right here, and I set up my x and y coordinates. And let's just break it into the x direction. So I know the x component of this one is going to be equal to the x component of this one plus the x component of this vector right here. Because we know this is a way that we can add vectors together. So if now I know that this x component is 0 because this is going straight up. It doesn't have any slant to the left or to the right. The x component of this one right here is, well, it's in the negative direction. It's going to be the hypotenuse, which is 10 times the cosine of my angle. And then the x component of my float with respect to the Earth is positive 6. Okay? So, and our goal here is to find this angle. If I can do the same in the y direction, if I wanted to, we don't know how big this y component is. We know that the y component of this piece is the sine of the angle times the hypotenuse. And then we know that the y component of this piece is 0. Now if I look at my two equations, I see that this one right here, okay, well, there's only one unknown. We don't know what theta is. So we can actually use this and we can solve for theta. And I get that it's 53.2 degrees. So there I've just solved a problem to give you the angle is 53 degrees, which is this degree. So I would say that is 53.2 degrees north of west, right? West is this way. If we go north of west by 53 degrees, that's the direction the boat has to move away from the floating device in order to move straight across the river if you measure its position from that spot on the Earth. Sometimes it might ask you to find this angle. How far west of north would that be, and what is that going to be? That's going to be 36.8 degrees. So it's also 36.8 degrees west of north is what the boat has to do, move away from that floating device, so that if we look at the boat from the Earth, it's just moving straight away like this. So that's one problem that we can use to solve relative velocity. I wanted to I encourage you to take a look again at those relative velocity problems that I had posted, and I also put up some solutions the other night, and to try to try those out again. And if you have any questions, please leave a note in the Edmodo for me, or email me, or come with questions on Monday. Okay, all right. Talk to you soon.